Okay. Let's get started. And yeah, so this time we finish the block matrix multiplication, and we start a little bit on this determinant of matrices. So important thing here, determinant is, well, it's a number. You can define on n by n matrices. And it's very important because it can tell you that whether a matrix is non-singular. And as a spoiler that we will prove today is that determinant of a matrix is 0 if only if A is singular. So for example, A is this 1, 2, 1, 2 matrix, and the calculation determinant, if you remember from high school, for 2 by 2 is this diagonal minus this diagonal. So it's 1, 2 minus 2, 1, and it's 0. And this will be a singular matrix because if you think about yourself of Ax equal to B, then it's x1 plus 2x2 equal to b1, x1 plus 2x2 equal to b2, because those two lines are the same. And so basically you are having either the same equations, or you have infinite solution, or you have or b1 not equal b2 and you have no solution. So it's very singular. Or I guess for our definition, if you say b equal to 0, then you always have infinite solution because you have two same equations. Okay. And okay, so that's a quick example of determinant. And once again, notation here, we use this vertical line as our determinant. Okay. And we'll straight into our definition of determinant. So we have this really complicated recursive definition. So as a definition, we'll expand our determinant from first column. Okay, so if dimension is 1, then our determinant is just whatever the number our matrix has, A11. And if dimension is bigger than 1, then we expand into determinant of a smaller matrix. So it's easier to see from this picture here. So we expand on the first column, and we multiply, and we have this multiplication of two things adding together. So the first thing is whatever number in this column. So this is A11, then A12, then A22. Sorry, the n13 to a1n, and then we need to multiply this cofactor. So minus 1 to I plus j, so it's just 1 minus 1, 1 minus 1, 1 minus 1, etc. And the determinant of a submatrix. And it's annoying that we don't have a name of this matrix. Maybe there is no official name, but I will call it cofactor matrix. Okay, so yeah. So this Mij, let's call it cofactor matrix, is n minus 1 by n minus 1 matrix. So that's why we can do recursive. We are going to go to a determinant of a smaller matrix, and its entry is the original matrix. But so when you expand Aij, then you delete the ith row and delete the ith column. And similar, Aij is here, you delete this and delete this, and remaining thing you combine into Mij. Otherwise, Aij is here, delete this, then you combine into Mij. Okay. But for now, we are just doing on the first column, so it's all deletion like this. Okay, so you got a whole bunch of Mij, then you calculate the determinant of it. Okay. So each term is element of the first column times the cofactor of cofactor, which is basically a determinant of the smaller matrix. And this delta Mij, we do have a name, is called minor. Okay. So I should not call it cofactor matrix. So maybe I should call this minor submatrix. Anyway. We have a name for the determinant of this thing, but we don't have a name for it. That's annoying. And yeah. Anyway, so minor is the determinant of a smaller matrix. Then you can recursively do the definition. Then you can, for each Mij, you can expand on its first column. Then once again you sum over those elements, and you have cofactors. So then you need to calculate the determinant of n-2 by n-2 matrix, etc. Then all the way until you have a determinant of one element, that's A11. Okay, and yeah, once again we have this definition of covectors. I guess we basically already defined, but anyway, so this is definition of the minor and the covector. So determinant of this minor submatrix is called minor, and this minor times -1 to the I plus j is called a covector Aij, and covector is pretty useful, so it was the name here, as we'll see at the end of the chapter. And anyway, so for example, let's see our 2x2 determinant as a covector expansion. So if I expand on the first, I'm saying it's wrong. So we actually, we actually expand on the first row instead of first column. Although we are going to say later that doesn't matter. Okay. So yeah, the definition is written as first row. Sorry about this. Yeah, so you expand on the first row. So you have A11, and its covector submatrix is 1 by 1 matrix, so it's just A22, and then A12. Then because it's a 1-2 entry, you have a -1 here, and the minor is a determinant of this A21, and yeah, and that's just A21. So you have A11, A22 minus A12, A21. And then we see that we can also expand on the second row. So you have A21, and now the -1 factor is a 2-1 entry, so you got a -1. And then the minor is this A12. And then you have A22, so now the -1 factor is +1. And you have minor is A11. Then, as we say, we can also expand on columns. So A11, the covector is A22, then A21, the covector is minus of A12. And also you can do the second column, it's the same thing. Okay? And then we have a bigger example. Yeah, bigger example. So determinant of a 3x3 matrix, then we need to reduce to 2x2. So we have A11 and its covector, which is a determinant of this 1, 2, 4, 6 vector. 1, 2, 4, 6 matrix. And then it's 5, and then we have a -1 vector, and then we have a determinant of this 3, 5, 2, 6, and then 4, and now it's +1, and the determinant of this 3, 1, 4, 5. And then you need to recursively calculate the determinant of those three things, and you know it's a diagonal thing, and anyway you will get -16. And you can also expand on the first column, and you will get the same number. And a small review on high school is actually like all possible permutation of those row and column. So you have 6 terms adding and subtracting together. So you have those 3 correct direction diagonal. So you have 216 plus 525 plus 434. Then minus 224 minus 536 minus 415. So there is actually an element-wise definition, but it's not how we. There is actually an element-wise definition of a determinant for any dimension, but it's out of the scope. So if you want to learn it, you can check Wikipedia. Okay. And anyway, so far any question? We'll stick with the recursive definition of a determinant. And okay, so if there is no question, then we have this theorem. I believe that we cannot quite prove because we are stuck with this annoying recursive definition. But anyway, well, this theorem is true, and you can prove pretty easy with the element-wise permutation definition, but but here we just believe this is true. So for every determinant, so as you have seen, we can expand on any row in the column. Okay. So although our definition is expand on first row, you can actually expand on any row in the column, and you will get the same determinant. So yeah, so this is quite important. Wait, oh, here I am. So yeah, any row in the column. Okay, so you can do determinant expansion on any row in the column, and you will get the same determinant. And yeah, we have seen some example that it works, but here we just claim that it works in general. Okay, and this fact is useful because you can simplify calculation a lot of time. So for example, now you can choose any row in the column. You can just choose a row in column that has a lot of zeros. For example, your A look like this, then you can expand on this column, and you see that most of them is 0, so you only need to expand on these 2, and the other thing. Then the other thing, you say there are also a lot of zeros, you just need to multiply on these 3, and you got things. So this can make your things a lot easier when you have a lot of zeros. Okay? And also, then we can prove that determinant of A transpose equal to determinant of A. And we don't write all the proof here, but you can prove by we can prove by induction. So we think about A like this, and A transpose like this. So every element transpose, and okay, so we didn't write down all the proof details, but we can say high level how this proof by induction works. So we expand A on first row, and expand A transpose on first column. Yeah. So you think about you are adding together those A11, A12, to A1n with those minors. And the N transpose, you are adding up the same element because it's transpose. So this row corresponds to this column. And so you're adding up the same A and the same minus 1 to the I plus J, and the determinant of this minor submatrix and the determinant of this minor substrate matrix. So this submatrix and this submatrix, they are also transposed to each other because yeah, you can just read the elements. So they are also transposed to each other. So this is where our induction works. So if determinant of this n by 1 matrix is same as the determinant of the n by 1 matrix, then we see a determinant of the n by n matrix is same as determinant of n by n matrix. So you can go from n equal to 1 to n equal, so you can go from n equal to 1 to n to whatever. So obviously a determinant of the 1 by 1 matrix is the same when you do transpose, because you do transpose of 1 by 1 matrix, it doesn't do anything. And yeah. And from there, you can prove the determinant of 2 by 2 matrix equal to the transpose, and 3 by 3, etc. Because when n minus 1 by n1, when every n minus 1 by n minus 1 matrix have the same determinant, have satisfied this equation, then you see the n by n matrix satisfy this equation. Just doing this expansion on first column and the expansion on first row and the expansion on first column. And anyway, here is the example of 3 by 3 matrix. So you see that you expand on those 3 is same as expand on those 3. Because you expand on 1, then you have a determinant of the 5, 6, 8, 9. And then you expand on 1, then you have a determinant on this 5, 8, 6, 9. But you know on 2 by 2 matrix, you do transpose, it doesn't matter because it's the same diagonal minus diagonal. Okay? And similarly, this 2 you get 4, 7, 6, 9, and this 2 you get 4, 6, 7, 9. Oh, I should do the same. So I should say 4, 6, 7, 9 here, and 4, 7, 6, 9. So it's a transpose. So the minor submatrix are transposed to each other. And similarly, these 3 you have the minor submatrix being this 4, 5, 7, 6, and you have C here. You have 4, 7, 5, 8. So you see they are transposed to each other. So if the 2 by 2 determinant satisfy this determinant AT equal to determinant A, then you see the 3 by 3 matrix also satisfy. Then you can say 4 by 4 also satisfy, etc. all the way to infinity. Okay, so we have a 2 property of determinant now. Any question so far? Okay, so let's keep getting properties. Okay, so the next property is a very easy proof, and it says if our triangular matrix, so lower than this line is all 0 down here, then the determinant of A is the product of just this diagonal. So the other case of diagonal doesn't matter. Here is A11 times A22 times all the way to A, and anyone want to say why? Yeah. And anyway, so this can be done by the thing we just said. We can do the, I guess you can do induction, but it's kind of obvious. And we can just pick the row in the column with most 0, so to expand. So when we expand, so we pick. Okay, so maybe let's draw here. Yeah. So for example here, so we can pick this column to expand. Then you see that you only need to do 1 times the determinant of this matrix. Okay. Then you do this column. Then the only non-zero is this 2. Then you have 2 times the determinant of this matrix. Then expand on this column. Then you have 3 times 4. Okay. So yeah, so you see that you keep picking the first column as your expansion, then you are only picking on the diagonal element. So it's just diagonal element multiplying each other. Okay. And the next property, okay, we actually have 2 properties here. The first one is pretty simple. We say that if a row or column consists of entire zeros, then its determinant is 0. And it's pretty obvious. You just expand on it, then it's all 0. So the Aij element are all 0, so it's all 0. And the second property is that if you have 2 identical rows or 2 identical columns, then determinant is 0. Okay, so this is more tricky to prove, and we prove by induction. So we say if you have this row, so for example we have these 2 rows are the same, then we say its determinant is 0, and what we do is we prove by induction until we are 2 by 2. Okay, so base case. So base case is actually 2 by 2 because 1 by 1 matrix cannot have 2 rows or columns. Okay, so in 2 by 2, how does this work? And well, it's either same row or same column, so it's either A B A B or A B B. Right? And you see that the determinant of both of these, I should write determinant, right? Determinant. So you either have A B or A B, and you see both of the determinant is equal to AB minus AB minus AB is 0. Okay, so 2 by 2 base case works, and I go to 3 by 3 is saying that we expand on the row or column that's not the same. So we expand, say, 1, 2, 3, 1, 2, 3. Then we expand on the middle part. Then we see so whatever this coefficient has times the determinant of those minors, so times the determinant of those minors of matrix. But you see those minors of matrix will have the same row and the column because they contain those 2 same rows. For example here, or in a column you can imagine the same thing. Okay, so but we already said the 2 by 2 matrix, you have the same row, then it's 0. So those minors will be 0, so determinant will be 0. So we prove that 3 by 3 you have the property, then on the 4 by 4 you can do the same thing. So on 4 by 4 you expand on the row column that's not the same, then you will get 3 minors that are determinant of 3 by 3 matrix that have the same row and column, so you know it's going to be 0. So by induction it works. Okay? Yeah. So the proof is pretty cool. I think the result is we should remember because you are going to use it on the just next section a lot. We will build on this to prove a lot of things. Okay, any question? We are very fast. Okay, so we already go to the checklist. I think we are a little too fast, so anyway, let's go to the checklist first. So things to remember. First is the definition of our determinant and the cofactor. So we have this recursive determinant that will expand. For definition, we say we expand on first row. And okay, let's jump back to the definition again. So we have this recursive definition. So determinant is element on those first row and times the cofactors of each element. Okay. And the cofactor has this -1 to the I plus j. So basically, it's going to be it's going to be 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Will depend on I and j. And times the determinant of the minors of a matrix. So this determinant of m, so this mij is whatever element you are looking at, then you delete the associated row and column. So remaining matrix is this mij, and you want to calculate determinant of it. Then it's a small matrix, so you do this recursive definition to get smaller and smaller mij. Okay, until you are 1 by 1. And okay, so where are we? Maybe 20? No. Okay. Yeah. So that's a recursive definition of determinant, and as we said, you can expand on any row or column. Okay, so although our definition is first row, actually you calculate on any row in the column is correct, and we didn't quite get a proof. And then we have a whole bunch of properties that we provide by induction. So first is determinant of A transpose equal to determinant of A. So basically just rearranging elements. And also determinant of the triangular matrix is equal to the product of its diagonal. Okay. And then we have pretty obvious properties that you have A has any row in the column that's all zeros, then determinant of A equal to 0. Then we have that if A has 2 identical rows in the columns, then determinant A is also 0. Okay. Any questions so far? If not, then let's go to a little digression. Let's say do I have? No. Okay, let's find a blank space. Maybe here. Okay. So let's see if I can do this. I still want to do this. So the permutation definition of delta A. So another definition of the determinant is delta A. So determinant of A is equal to this summation. Okay, so why do I keep talking about permutation? So you are summing over some permutation. Let's call it. Okay, we have BT as a sigma. So sigma is the permutation of an element, and then we have this pi. Okay, let's not write that. So we sum over all possible permutation. Then we have this product of elements. That's kind of like a 3x3 example. So we have A1, then sigma of 1, then A2 sigma of 2, to An sigma of n. So sigma of 1, sigma 2 to sigma n is a permutation of 1 to n, so it's also going to be a number of 1 to n. So if those all producting together, and then we need to tie the factor, that's very weird. That's a sign. That's the sign of the permutation. That's very hard to define without talking more about combinatorial sign of the permutation. Okay, so permutation is like this. So permutation can be written as string because you can think about you have 1, 2, 3 to n. Okay, so we have and then we are permuting to number. So maybe we just write whatever string. Maybe like 2, 3, 4, 5, etc. To whatever, right? Maybe that's okay. So maybe let's give a better example. So permutation example. Okay, so this is extra. So example of permutation. So maybe 1, 2, 3, 1, 2, sorry. Maybe 1, 2, 3, 4. It's so hot. And then you do whatever permutation. So maybe you have 4, 2, 1, 3. So you are permuting 1 to 4, and 2 to 2, and 3 to 1, and 4 to 3, etc. Okay. And yeah. So it's so you are thinking about those 4 numbers, you permute to whatever ordering of them. And example of S3. So the all possible permutation of 3 things is 1, 2, 3, and 2, 1, 3, and sorry, this is not the order I want. 1, 2, 3, and 2, 3, 1, and 3, 1, 2, then 1, 3, 2, 3, 2, 1, and 2, 1, 3. So those are all possible 6 permutation of 3 element, and then you will see that. So the sign of those are plus, and the sign of those 3 are minus. So this corresponding to the 6 terms you have on the 3x3 determinant. Okay. So you have 3 things with positive sign. That's this, those 3 times those 3 plus those 3 plus those 3. Anyway, those 3 plus those 3 plus those 3, and yeah, and the other direction diagonal correspond to the other permutation. And on the higher diagonal, you still have all the permutation. So you have n factorial terms. and there is a way to define those signs there, etc. And yeah, you can derive everything in this permutation definition, but here we are using the cofactor expansion definition, and they are equivalent to each other. So that's some digression. Yes, yeah, that's some digression that you don't need to know, but it's pretty cool. Now to learn it, then you can read more material. Okay, and anyway, let's go back to our. We still have time, so guess I'll keep proving more things. So we have 2.1 here. Yeah, and yeah, reminder again. So we have now some interesting property here, and so we have proved that determinant of A transpose equal to determinant of A, and determinant of a triangular matrix is just the product of the diagonal elements. And for n by n matrix, if row and column are all 0, then determinant is 0. And also, then this is less obvious one. If the A has two identical rows and columns, then determinant is 0. Okay, so we are going to use this one to prove a lot of things now. Okay. Basically, we are going to build from this to characterize when A is singular. Okay. So yeah, let's go to the next section. 2.2 more properties of determinant, and and we start with this quite technical lemma. So we want to say something really funny. Okay, so we think about this thing. Okay, it looks really like determinant, but it's not. Okay. Okay, so this thing looks really like determinant expansion, but so this thing has a different I and a J here. Okay, wait, sorry. So you need to notice that we have I and a J here. This is a function of I and a J. And so you see this is really like a cofactor expansion. You have those small a times big A. But we have a different I and a J for this small a and big A. Okay, so in the cofactor expansion, you have I equal to J. So when I equal to J, this is just a determinant. Okay, and yeah, so we are thinking about so for those small a is the so if I equal to J, you are expanding on ith row. Okay. So I should say this is like. So this is like a ith row with the jth row cofactor. Okay. So it's like a ith row inner product in with the jth row cofactor. So I have different I and J here. And this lemma says that if I equal to J, then obviously this is expanding A on the ith row, so this is just determinant of A. But if I not equal to J, then this is actually 0. Okay, so this is a really weird lemma. You might ask why do we want to do this, but it'll be going to be useful later. Okay, and yeah, as we said, this is the expansion of the ith row, so I equal to J is easy. And if not I not equal to J, then Y is 0. Then that's why we need to use the weird property we had before. So I not equal to J, then we can think about we just replace the Jth row by ith row. Okay. So say I is here, so we replace Jth row with ith row. Okay. So we have a different matrix A star here, and oh wait, well Okay. It's annoying. Okay, then this thing, so let's go back. Then this thing is you can think about this thing, is the determinant of A star. Okay? Why? Because I not equal to J. Is it? Let's see. The J0. Okay, yeah. So this is a determinant of A star because you expand A star from here. Expand on the J0 here. Okay. So yeah, so because this thing doesn't depend on the original J0 at all. Because when you are calculating the cofactor on the because those cofactors on J0 doesn't look at the J0 of A, right? Because you keep deleting J0. And so you can do this replace, and you can still calculate this thing. But anyway, you think about this A star matrix that kind of replace J0 by I0, and expand here. So all the small Aij will be, well, it will be those AI1 to AIN, right? AIN, okay? So you have AI1 to AIN, and then the cofactor will be same as, so the cofactor of A star on J0, as we say, is the same as the cofactor of A, because you keep expanding here and you didn't see that you got replaced here. Okay, and yeah, so the cofactor big AJI will be same as the cofactor here. So okay, so let's write this once again. So you expand here, then you actually get AI1 times big AJ1 plus AI2 times big AJ2 plus AIN big AJN. Okay, so here we are using that you replace this row, then the big AJI equal to the big A star JI, etc. And okay, so you expand the A star on this J0 is the same as the expansion we want to calculate, and it's 0 because of the property we talked about. Now this A star has two rows that's the same to each other, because we just, by construction, we just make these rows and these J0 same as this I0. So it has two rows that's same as each other, and so the determinant of A star is 0. And so we prove this really weird property that you expand I0 with the J0 cofactor and it should be 0. Okay, and then we build on the next thing. The next thing we want to do is we want to show how row operations change the determinant of a matrix. And so we do it in reverse order. First, we see how the row operation 3 changes the determinant, and it actually doesn't change. Okay. Okay. So what's the row operation 3? Row operation 3 is you adding one row to another row with some multiple, and yeah. And let's look at this first. So we think about, we do determinant of this elementary matrix that is excuse me. So we are adding C times of the I0 to the J0. Okay. And okay. So let's draw something here. So we have I0 here, and so think about this I and the J, and we add this C times here. Okay. So it's like CAI plus AJ, no? Okay. So we add, so we add I0 to J0, and so the J0 now becomes C times I0 plus, so I think we use vector plus AJ. Okay, and and now we expand, now we calculate determinant by expand on the J0. And so the cofactors are all those AJ plus C times AI, okay, and times the cofactors of the J0s, also the AJ1 to AJN, and so then we just do by linearity, so those multiplications, so everything is scalar, so you just multiply it out. And so you just have this small aj times big aj, those part. And so you group these jj terms together. So you have small aj times big aj, small aj times big aj. So this is the original determinant. And then we have this weird term. Yeah. That's c times is small ai times big aj. So small a I1 times big A J1, then small a I2 times big A J2, etc. all the way. Okay, so those summing together, and then this is why we need to want to prove this weird lemma. Okay, so this is exactly this. So it's one row times the cofactor of another row. That's not the same as each other. I not equal to j. Obviously, when you do row operation, you are doing different I than j. And so by the lemma that we prove with a lot of effort, that we use the determinant of two rows, same row are 0. So just by the previous lemma, then this term should be 0. Okay. So lemma. Here we use the lemma that we prove. So this weird addition that doesn't change your determinant at all. So we prove that this is very complicated, the most complicated row operation. So it's one row, multiple of one row to another row, then the determinant doesn't change at all. Okay. So this is the most technical thing today. Any question? So we go a long way. So first we come from this recursive proof saying that if A has identical two rows and columns, then its determinant is 0. Then we go to this substitution proof saying that we have this weird term where we are basically doing inner product of one row with the cofactors of another row, and it should be 0 because you see the determinant of a matrix that has two same rows. And then we use this to prove something really cool. We say that we can do this row operation on the determinant. This operation 3 on determinant, and it doesn't change the determinant at all. Okay, so this is a very important fact. And you can imagine we are going to teach you how all the row operation change the determinant, and then you can use row operation to simplify the calculation of a determinant. Right. Here's we can also change consistency. So from this thing, then you can also from this, although the logic now is a little circular, but we can check consistency. From that, you can derive this easily. So now you kind of see a reason why. So if we believe that, then we change consistency, then we have that. You have two same, okay, so you have two same row, then you can just add a -1 of one row to another row, then you get a row of zeros, then we know that the row of zeros then determines 0. So that check by consistency, and then you have same columns, then you can do the transpose first, and to get same rows, and you know same rows should give you 0. Okay, but this derivation is circular now because we are building from this fact the two rows are the same, then any row operation doesn't change the determinant. Okay, if the two same row determine 0, then any row operation doesn't change the determinant. Okay, and something extra that will also be useful later is we can check that determinant of the row of E times A is the same as determinant E times determinant A. Okay, and here E is a row operation. And so determinant of EA equal to determinant A, that we just proved. And then determinant E equal to identity is something we can prove easily because determinant E, so I write this wrong. So I should say E is diagonal. Okay, so E is diagonal. Right. So determinant of E can be calculated easily. And so E is, so you remember how it looks like, it's like a diagonal of ones and C somewhere, okay, and O 0 otherwhere, okay, and C might be up here or down there, doesn't matter. So yeah, and yeah. So if C is down there, then you do the transpose of E to take C up there, then you get a diagonal matrix. And we know for diagonal matrix, the determinant is just a product of all those diagonal elements. It's all 1, so the product is 1. Okay. And okay, and I think it's a good time for a break. Any question? No? Oh, I'm messing up the ordering. Okay, that's why I didn't see. Okay, yeah, and yeah, on break, sorry, I'm missing a slide, but this is the text part of the lemma 2.2. But hopefully, I messed up the ordering of the slide. Yeah, you can look at this. Oh, so hot. Yeah. It's so hot.你说这个雷马的部分吗？对吧？不对，这个可能我想想看，用这页比较容易懂啊。就是我们做出这个 A star 嘛，可能直接在这里画吧。我们有 A 嘛 ，A 等于 whatever， 然后我们变出一个 A star 这样子。A star 是可能跟 IJ 有关的东西，不管。对 A star 是说，对这里有个 AI， 然后这里有个 AJ， 然后不对，画反了。我们刚画的是 J 在上面嘛，这里有个 J0， 这里有个 I0， 然后我记得我们是说，我们把 J0 变成一个 I0 的东西。对，这两行是一样的。就你总是可以硬写嘛，就是你把这一行擦掉，然后全部改写成 I 这样。对，这两行是一样的。然后那我们知道 delta A star 等于0嘛？就是上面写的，应该这样写。就 determinant A star 应该是等于0的，因为这两行是一样的。那这个东西其实就会等于我们刚刚这乖乖 expansion， 就是你 expand 这里的话，就会等于内串的东西。因为就你想这里也所有东西，所以这里 这里的 small a 就是这个 small ai one， 然后 small ai two， 因为这里的这一行已经被换成 ai 了，所以你是放这里，那它的这个 element 就是 ai 多少东西。那它 factor 的话其实没有变的，因为你只把这一行换掉。但是你每次在算那个 big A 的时候，你会把这一行给切掉，所以其实那些 AJ， 然后所以你要，对，所以我写完，对 A， 我可能写慢一点吧，你 expand on 这里嘛，所以这个东西你会有 A star 的 J1， 可是我写不出来，就这样，OK， 所以我抱歉，这个是这样子 ，A star 的 J1， 然后 A star 的 J1 加上 A star 的 J2，A star 的 J2 加上打，然后 A star 的 J1 会等于 A 的 A1， 因为我们这样弄的，然后 A star 的 J1 就还是 A 的 J1。因为你把它切掉没差这样。对，然后所以这个怪怪的东西就等于0。OK， 所以有听懂吗？有问题吗？
它这个是指
对，是它的。如果 A 是我们之前传，等一下 A 是 non-singular 的话，有equivalent to I。看起来可以啊，我想想看，可以啊，可以。这一题是有别的证法，但我觉得这样子也可以啊。我想课本想的证法应该是那个吧，你去解 ax 等于0，然后去找到这个手术圈之类的，然后就这里这样子就一大堆手术圈。
然后就可以根据那个对式然后说它是。
对啊。然后 ax 你可以看成是 column 的相加之类的，所以，
然后这边就是因为这个东西对吧？这个东西，所以才能这样写。
了解 A star 的这一关。因为有，就是这里比较复杂，就是有这两个 matrix 这样。所以这里我写一下好了。A star 的 J1 A J1 加上 A star 好热。这一题。第一题 A， 然后 看起来也还可以啊，虽然你比较辛苦一点。没有啊，就是他已经跟你讲 B 是这个风了，所以你就把它丢进去比较快一点，但是也差不多。
应该先证明他会拿 C。
啊？non-singular 只要有一个解就可以啊，所以如果你这个丢进去凹得出来的话，那就可以。但你这样也可以啊，只是比较辛苦。他不是已经告诉你说他应该要长这个样子吗？所以其实你一开始就可以做 B2 的零。
可是这不是要我去证明他会长那样？
就找到有一个这样的话，那就可以啊。但你这样真的也可以啊，你就是比他更努力一点这样子，然后所以后面
这个用起来会合，然后就可以用。
对吧？因为 non-singular 就是我们有 inverse 嘛，那你当然是找到 inverse 的话，那就可以了。而且 inverse 我们还知道是 unique 的，所以你知道找到是，所以如果这个可以是 inverse 的话，那你就知道 inverse 就应该要长这个样子。
所以我就带进去，然后说，这个他会。
对啊，但你都写这样子，那也可以，只是你这样比较辛苦一点。
还不知道是什么可以。
对啊，所以 C 一样，你这里应该你也有解这个 B1 2吧？你有吗？应该有啊。所以你这里还是就解出了 B2 那里嘛。然后 C 你有解出来吗？应该要有吧。你要怎样去？
会不会这样子讲啦？
你是说什么？我看一下啊。所以其实我也没有太认真看，所以这两个。我看一下，所以这个等于0，然后这个跟这个就是那个负1的东西。对，所以你上面就是解出了说你要是这个形式，所以最后还有一个 C 的应该要是怎样？其实我也没有认真算过，can be 0，所以你要证明说你可以找出 C， 让它这个。所以你要这个，那你还是要解出 C 是多少？虽然你说 can be 0 no what 嘛，但是。
但我不知道这样写是可以。
这样写看起来不太可以啊！你要说这个东西为什么可以 be 0啊？你现在还剩什么东西可以调？为什么你有 A1 2？ 哦，对，的确有 A1 2 A2 对啊，所以现在这3个东西都 fixed 的嘛，所以你要说这3个东西都 fixed 的，那也 B1 2可以真的把它解除0啊。你现在只剩 B1 2，然后就是这个 C 的东西嘛。对，要我给你更多提示吗？你这里对啊，你这里不是有其实这个题目有点奇怪。对，所以第2题你会解出 C。对 ，OK， 所以我好像讲的有点混乱，我想想看这个逻辑要怎么讲。所以 A must be trans and singular。所以好像你这样写比较对，因为我想直接把 C 解出来。我想这2题一起解。那如果，OK， 所以应该是说，所以你到这里的话，你就，可是它很奇怪。等下我想一下，我自己逻辑有点混乱，这一题有点那个。所以你2的部分，你到这里就已经证完，你到这里把2的部分证完了嘛？就是你假设是这样子，然后。
我只有写出这3个会长这样。
对，你写出那3个会长这样。但是我想想看，你这样子有办法直接 argue 到这场 singular 吗？好像没有办法。所以这题目有点奇怪。我想想看，我有办法 argue 它是 non-singular without determinant C 吗？我就让自己把 C 解出来比较简单。好吧，我想不到更简单的解法。我觉得，对啊，我觉得，
对，
对，对，那就
所以它就是
对啊，
所以先从第2题开始。
对，好像要先解第2题才能解第1题，它就有点奇怪，抱歉。对，它的题目有点奇怪。 Okay, let's get back to our class. And so it's really hot here. And yeah, so people seem more confused about lemma 2.2.1. And here, let's say again. So the proof, the page we omit is this. So we say we define this A star as you replace the jth row of A with the ith row of A. So A star is this matrix which has two same row. Because this row is jth row is small a I1 to small a in. This jth row is same as this ith row. And as we say, then the determinant of A star must be 0 because it has same two row. And then we expand the A star on jth row. Then if we write down formula, it should be the J A star Ji times big A star J1. So it should be this expansion. So the small A star J1 is the J1's element of A star. So it should be this element times the cofactor of this element. And this element times the cofactor of this element, etc. Okay? So it should be this A star J1 times big A star J1 plus A star small A star J2 times big A star J2 all the way to small A star Jn to big A star Jn. And then we think about how those things are related to the A without star. So A star of J1, as we know, is we are copying it from big A's ith row. So it should be small a I1, and similarly, this A star of J2 should be A of I2. So the J become I, and all the way. So yeah, so the A star of JK should be A of IK. And also this A star of J1 should be just A of J1. Because I'll say A star and the A just change from the jth row. But when you're calculating the jth row cofactors, you are always deleting the jth row. So the changing of jth row doesn't matter. So this cofactor of A star on jth row should be equal to cofactor of jth row A. So then you go back to this weird equation we had before. So A of I1 and big A of J1 times A of I2 big A of J2 all those things should equal to the determinant of A star. Okay, any question? Okay, yeah, this is a proof. And okay, let's go back to our elementary operations. So we go this in reverse order because we start with the most technical one. And then we use this technical lemma. Then we see that when you do the addition of rows, you don't change the determinant at all. And also determinant of EA equal to determinant of E times determinant of A. This will be basis of another theorem that we are going to prove. And okay, then the other one is row operation 2. Row operation 2 is you are multiplying a row by a non-zero constant. And this proof is pretty easy. So that's the first thing, a determinant of this, the corresponding elementary matrix. Well, the elementary matrix, look at this, is just diagonal. Whole bunch of 1 with the alpha in the middle, and it's diagonal. And yeah, so whatever you do expansion, etc., and you see that you are just multiplying the diagonal together. And so determinant should just be alpha. And then you think about determinant of A acted on by this elementary operation. And well, the matrix that after you do the elementary operation is just like this. So it's the same matrix with one row multiplied by alpha. Then you just cofactor expansion on the ith row. then you see that, so every term just get multiplied by alpha, so you are just multiplying. And you can take all the alpha, and you see the determinant is just alpha times the original determinant. Okay, so it's pretty easy. You're just multiplying by a constant vector alpha. And once again, determinant of E times A is alpha times the determinant of A that we just proved. And we know alpha equal to determinant of E, so it's equal to determinant E times determinant A. Okay. So this one is easy. And the last one is actually a little tricky to prove. Is excuse me. Row operation 1 is you exchange two rows. And okay, and here we cheat a little bit, and we use row operation 1 to prove this. Okay, actually we use row operation 1 and 2 to prove this. Okay, and here we do a proof by example, but obviously you can generalize it. And okay, so we are actually going to use the other two row operation to get this row operation. Okay, so we kind of want to exchange the second row and the third row now. And so what we do is we add a -1 of third row to the second row. So basically subtract the third row from the second row. Okay, so then we get another matrix like this. And we know determinant of this should equal to determinant of this, because the third row operation doesn't change determinant. And then we add the second row to third row. Okay, so maybe let's write down things in a little notation. So we think A as its rows, so we have A1, A2, A3. So those three row vectors. Okay, and so here we subtract this, so we have A2 minus A3 here, and A3 down here. And then we add this, so we had A2 minus A3. A2 minus A3, and then we add this to the third row, so A2 minus A3 plus A3, so we got A2 here. Okay, so now it's A2 here. Okay, and then we subtract this A2 from the second row again, so now we get A3 minus and A2 here. Okay, so yeah, so we are close to what we get. Now we change 2 and 3 now, but we have extra minus sign, so we just multiply by the minus sign. Then we get A3 and A2. Okay, A3 and A2. Okay, yeah. So this is how we change the second row and the third row. Okay, so we do a whole bunch of addition, subtraction, and then we multiply -1. Okay, and as we said, so the previous addition, subtraction operation doesn't change the determinant at all, and the last one will multiply -1. So as we know, multiply by -1, you get -1 your determinant. So we see the final matrix, which is you change the second row and the third row has a determinant that's -1 of the original matrix. And you see here that the location of these 2 and 3 doesn't matter at all. So in changing any two row in the column, should give you this -1 here. Okay. So yeah, so this -1 here important. Okay, this is -1. And yeah. And then once again we want to check the determinant of EIJ. How determinant of EIJ, what's determinant of EIJ, and here we cheat a little bit, although you can also do cofactor expansion and get the same result, but here we do a little cheating. So we say the determinant of EIJ is the determinant of EIJ applied on identity matrix, and that should be -1 times the determinant of identity matrix. Okay, so here we are doing cheating. Yeah, so we use a bit, well, not quite, but we are doing another way of this argument. So we say determinant of this thing, then we use the relation we just proved. So it's just -1 times the determinant identity, and we know determinant identity equals 1, so it's just -1. And so in general, determinant Eij times A is -1 times A. And so we just prove that -1 is determinant of Eij for any Ij, so that's the determinant of E times determinant of A. Okay. So for all elementary operation, we have determinant of Ea equal to determinant of E times determinant of A. That's really cool. So here's the summary. Determinant of Ea equal to determinant E times determinant A for any elementary matrix E. And determinant of E, we have 3 different types. So if -1, if you are interchangeable in the column, you get a -1. And if you multiply by alpha, then it's alpha. And if you are adding or subtracting row from another row, then this E is 1. You don't change the determinant of A. Okay, so let's look at the summary and illustrate this. Any question? Okay. Well, no question, then okay, let's go to the other theorems. Okay, so finally our important theorem. The spoiler we had today, we say a matrix A is singular if only if its determinant equal to 0. And yeah, so here that's why we keep talking about elementary operation. So once again, we can do our favorite reduced row echelon form. And actually, we don't need to go to reduce, we just go to row echelon form. So we say, so for a matrix, we can always make it into row echelon form. And we apply a whole bunch of elementary operations. And then we use this nice formula saying determinant Ea equal to determinant E times determinant A. And yeah, so determinant of this row echelon form equal to determinant of all those row operations times the determinant of A. And then all the row operations here should have determinant non-zero. Yeah, because you don't multiply alpha with 0. Okay. Yeah, so those are all non-zero. So those are all non-zero, so determinant A equals to 0 if only if determinant U equals to 0. Okay, so we change this thing to determinant U equals to 0. And then we just need to see where determinant U equals to 0 if only if A equals to singular. And it's pretty obvious. So we just go from the A part to delta U part. So if A is singular, then we think about its row echelon form. Then it must contain a row with all zeros to make there some free variable. Okay. Yeah, here we are using A is n by n. Okay. So maybe let's draw something. So A is singular, then you want some free variable. So there is some variable that you got skipped. So you must yeah. So you think about you must skip some variable, then this part will have the height lower than its width, and so you get the end part with all 0 here, because you need to skip somewhere. Yeah. And then because you have the last row with all zeros, and yeah, because you have the last row that's all 0, then the determinant is 0. and otherwise is non-singular, then you know you are not skipping any variable, and actually, yeah, and I think our anyway, yeah. So yeah, if it's non-singular, then you know you're not skipping any rows, and then you reduce the original form look like this, and from our triangular calculation, triangular theorem, we know this U is a triangular matrix with all ones here, so delta U equal to 1 is not 0. Okay? So yeah, so here we prove our theorem with these elementary matrices and row echelon form. I think if we do reduce the row echelon form, then it's even stronger, even easier. But anyway, yeah. So here is one of our big theorem. So even if you don't remember the proof, you must remember the result. A singular if only if determinant A equals 0. This is must memorize. Okay. And here we also see that we have a way to calculate the determinant. Sometimes it's faster. Actually, I think it's kind of always faster when A is big. Okay, because you do Gaussian elimination here, then okay, let's calculate complexity a little later, and anyway, so we can always do row operation. We can go do row operation to reduce A to this row echelon form. So multiply a whole bunch of elementary matrix, and get A equal to row echelon form. And then you see that if you get this row echelon form, it has a row of zeros, then you know A is singular and determinant A is 0. Otherwise, A is non-singular, and you know delta U equal to 1, and you can just okay, and you can just calculate delta of A as inverse of delta of all those elementary operations. Okay. So here's a way to calculate the determinant of A, and we are computer science, so we can think about this is actually a little faster. So how many calculation you need to do here is, so here you are doing Gaussian eliminations, and you are doing Gaussian elimination, and so here is digression. So here number of steps is about order n cubed, and if you do cofactor expansion, then number of steps is about order. So you have n times n minus 1. So so you have n turns when you do expansion, and to n minus 1 and n minus 1, for each n minus 1 cofactor, you need to do n minus 1 times n minus 2 1. So that's about order n factorial. And so you see this is actually a little faster, because actually a lot faster when n is large, because it's polynomial in n, and if you do cofactor expansion, it's n factorial. Okay? So yeah, this is faster when your n is large. But that's something else. And yeah, anyway, you can do this a little faster, but I think it's the same. you can just reduce to a triangular form, so you can not. So in the row echelon form, remember we want the diagonals to be O1, and you can skip the making diagonal O1 step, and then yeah, you will get into the triangular form T with non-zero element, and you can get a similar you can get yeah, and yeah, you can get a similar formula. I guess here the nice thing is if you don't do that, then you only do row swapping and row addition subtraction, and rows E only have determinant +1 or the -1. And so here you have plus minus depend on the number of swap you do. So this is plus -1 here is the number of so it's -1 to the number of swaps. Okay, this is -1 to the number of swap. And yeah, and you have those T11 to T1, and that's the diagonals of your triangular form. So you have this T, that's like a T11, T22, T11, T22, to Tnn. Okay. So yeah, so this will make your calculation even easier a little bit, but doesn't change too much. You can also just multiply by alpha and make it O1, then know your alphas. Okay. And anyway, the key here is you can do this Gaussian elimination and make it into triangular form. Then you can calculate your determinant a little faster. Okay, so here's the example. Our 3x3 example here. So I want to calculate this determinant. 2, 1, 3, 4, 2, 1, 6 minus 3, 4. And so as we say, we do Gaussian elimination. So we add the first row. So we add the first row and times -2 to the second row. So we want to eliminate this 4, and we want to also eliminate this 6. So add this one down here, and we get this thing. And -3, so it's -6, and it's extra -5, -5. And then we see a 1 here, then we want to make this 6 up here, so we exchange those two rows, then we get a -1, and then we see that we are already in diagonal form, so it's just this 2 times -6 times -5, and then times the -1, so that's our determinant. Okay. Any question? Yeah. Okay. So that's a nice way to calculate determinant. And then we go to the next important theorem that you don't, even if you forgot the proof, you must remember that determinant A B equals determinant A times determinant B. Okay, very important. So the two most important theorems: first, A is singular if only if determinant equals 0. The second one is this: determinant AB equals determinant A times determinant B. And okay, so we have proof, and but we need to go into two cases. So I guess the first is the easy case. So if B is non-singular, then as we say, B can be written as the product of elementary matrices, because you can have a whole bunch of elementary matrices to make B equal to identity, right? Yeah, that's one of the 1.5.2 thing we prove. B is non-singular. B is a product of non-singular product of elementary matrix, and then we just use the version of this theorem on elementary matrix that we have proved when we do elementary matrices, right? So we can kick it all in one by one, and we see delta AB equals to delta A times delta of all those elementary matrices, and then we can group those together because yeah, because you can matrix on elementary matrix, and you have delta of all those things together, and that's just delta p. Okay, question about the easy part is because we have this. So for elementary matrix, we can kick them out and in very easy. So we can get this 1 out, then the 2 out, etc. Then we can get this 1 back, and then we can add 1 and 1 back together. So we can add this one in and this one in, etc. And finally, that's delta p. Okay, so that's an easy one, and there is a little more complicated one that we a little more complicated one that we have a compressed proof here. So if B is singular, and and first we need to show that AB also singular, and here we have a really short proof here. So why is it B singular and AB also equal singular? Because we think about how ABX equal to 0 have, how many solutions ABX equal to 0 have. And so from B is singular, we know that Bx equal to 0 is non-trivial solution. Okay, so maybe in this way. B is singular, then there exists x not equal to 0 such that Bx equal to 0. Okay, and okay, so that's from B singular, and from that, then you can multiply A on both parts. Then you see that ABX equal to 0 for this non-zero x. And then you can group AB together because matrix multiplication is associative. Then you see AB times this non-singular x equal to 0. And so you know that AB is also singular. Okay. And yeah, so B is singular, AB is also singular. So that's like I should do in homework exercise. Anyway. And yeah, so we have a small theorem in this proof, but with this thing, then we know that determinant of AB equal to 0 because from the previous, from our previous theorem we know AB. So we know AB is singular, so its determinant is 0. And determinant of B is also 0, so whatever determinant A is, determinant A times determinant B equals 0. So both of them equal 0 and they equal to each other. Okay. We are a little faster, so I just finish this chapter. Anyway, so here is the checklist. And as we said, the two most important theorems here that you must memorize even if you forgot its proof. The result you need to memorize. A is singular if only if determinant A is 0, and determinant of AB equal to determinant A times determinant B. Okay. And another thing is determinant only defined on n-by-n matrices. And then there are interesting lemmas we prove here. So first is this weird cofactor lemma where you have the cofactor on this row times the cofactor on ith row times the element of the times. So you have cofactor of jth row interpolate with ith row, then you see this determinant if I equal to j and it's 0 when I not equal to j. And then we see that the determinant of elementary matrices is equal to this -1 if it's a swap, and alpha if you are multiplying a row with alpha, and it's 1 if you do addition and subtraction from a row. And so from here, and also now you can go from the other way. So from determinant EA equal to determinant E times determinant A, then you know how each row operation will change the determinant of matrices. And here we can also, okay, So here also something pretty important you can calculate. So from here you can calculate delta A. From calculate delta A by Gaussian elimination. Okay, so you can just do row operation on A to make it into a triangular form and then calculate the determinant from there. Okay. We have 17 minutes. Let's first, do any people have question? Here we have a lot of property on determinant. And should I just finish? I think I can probably finish chapter 2 now. Why not? Okay. So if people have no question, let's keep going. And lots. Okay, let's talk a little bit about the additional thing. Oh, what's this? Pretty heavy load. I guess next time we're also going to see this. Let's show you. Let's flash on the next session a little bit. So next time we'll. But this is not one class, so. But anyway, next time we'll start here and then maybe go to chapter 3 a little bit. And anyway, so with all these determinant, and we can also calculate the inverse of a matrix with this Kramer formula you probably know from high school. Okay. So we can define this adjoint matrix, which is writing down all the cofactor of A, but with a transpose here, so we need to be careful. This is A21 here and A12 here, and but for usual matrix you have. Okay, so but for usual matrix you have A12 and A21 here. So you see this. This is a transpose of cofactor in their corresponding positions. Okay. So anyway, you can define this adjoint matrix. That's all those cofactors, and then remember we have this funny kind of orthogonal relationship from our weird lemma. That we have the ith row of A and the jth row of the cofactor. Inner product I equals 0, and then you use this, and then you think about this matrix and this cofactor matrix, and you see that there is a diagonal matrix with all the determinant, and okay, so you just determinant times identity, and you see that this adjoint is actually very similar to A inverse, and yeah. And yeah, so you can find A inverse by writing on the adjoint matrix, then divide by the determinant. And this is where you get a 2x2 formula that you probably have in high school. So you have A, B, C, D. Then you have your ADJA transpose equal to this DABC, right? That's all the corresponding minor matrices, and then you have ADJA equal to DA. Oh, I forgot a minus sign. There should be minus sign here. AD and minus C minus B. This is probably some formula you learn in high school. Then you divide this by determinant, you get A minus 1. And okay, so something here something. And something we check here once again is that you see why this should be not 0 for non-singular matrix. So only for determinant not equal to 0, you can calculate a minus 1 with this formula. And obviously, when determinant a equal to 0, you don't have a minus 1. So that's also consistent. Okay. And yeah, so we have an example, and example of a bigger drawing A. And as we say, drawing A, you need to remember you need to do the transpose. And so that's for A inverse, and also there's a formula for solving A is equal to B by calculating determinant, and that is you want to calculate the determinant of AI, which is so you have x equal to anyway, so it's the determinant. So xi will be determinant AI divided by determinant A, where determinant of AI is AI is you put the ith column of A into you replace the ith column of A with all those B. Okay. So that's another way to solve A minus 1 equal to solving Ax equal to B. And yeah, but once again, this only works for non-singular A. Okay. So this only works for non-singular A because you need to divide by determinant A. And if it's singular, then it's really weird. Yeah. But this will solve for the unique solution. And the proof is more complicated. And yeah, proof will go next time, although we have 10 minutes, so we probably have time. But I think that's enough for today. It is a little flashing of what we can do with determinant. And for today, you need to memorize those two results, very important. A singular if only if determinant A equals to 0, and determinant AB equals determinant A times determinant B. And also you need to know how elementary operation, row operation do on your determinant. So swap row in the column, you got minus 1. You multiply a row by alpha, then you got you got your determinant multiplied by alpha. And you do row addition or subtraction, you don't change your determinant. And also some property in 2.1, I believe it's here. Okay, so reminder, some properties, determinant of A transpose equal determinant of A, and you can do your cofactor expansion on any row in the column. And if triangular, then your determinant is just product of diagonal. And then if you have a row and column, all 0 is 0. And the last one, you can kind of go from this thing and the elementary operation we have, that is, you have two identical rows in the column, then determinant equal to 0. And okay, so I think we can end a little faster today because we are good on our schedule. And yeah, so see you on Wednesday, and we'll finish on determinant and maybe go on chapter 3. Okay.